This is the gas stoichiometry lab. And we have some equipment here to talk about. We have a long, skinny gas collection tube called a eudiometer tube. Now, this is different from another long, skinny tube that we'll use this year called a burette tube, in that there's a closed end at the top. I have a ring stand with a clamp that I can use to hold the tube in place. I have some deionized water. I have some tap water in a large beaker, which you'll see why we need that shortly. We have a thermometer. We have a piece of string. And we have a very small, perhaps hard to see, strip of magnesium that has been weighed out for us. We know that the mass of this strip of magnesium is 0.025 grams. We have some 6 molar hydrochloric acid, which is going to react with the magnesium. And we have a rubber stopper that fits into the eudiometer tube, and it has a hole in it so that it can equalize pressure inside to outside the tube. The first thing that we'll do, because it takes a little bit of time, is stick the thermometer into the tap water. And then, as we follow the directions, we're going to pour 10 milliliters of hydrochloric acid into the graduated cylinder. I'm going to then carefully add the hydrochloric acid to the long, skinny eudiometer tube, and making sure that the closed end is at the bottom so that the liquid doesn't spill out. Get all of it in. I'm then going to take the wash bottle with the ionized water and fill the eudiometer tube the rest of the way to the top. It's okay to overfill and to spill because the acid is at the bottom of the tube, and the water, which has a density or slightly less than that of the hydrochloric acid, is at the top. So we're going to spill and overfill, and that's okay. Next, we'll take our piece of magnesium, and I'm going to carefully tie the string around the magnesium so that it makes a little knot. Just something to keep it in place. I'm going to bend the magnesium a little bit so that it can fit into the tube. The reason the string is there is so that the magnesium doesn't just float off into space. It's not that the reaction wouldn't happen if it weren't anchored, but you'll get a more vigorous and quicker reaction if you do anchor it in place. Next, I'm going to add the rubber stopper to the bottom, the open end of the tube, which right now is at the top. And in doing that, I spilled a little bit of water out, and that is A-okay. So we've got our reaction prepared. At the bottom of the long, skinny eudiometer tube is the acid. We've got about 45 to 50 milliliters of deionized water on top of that. We have a piece of magnesium anchored to the top. Right now, it's the top of the tube. I'm going to flip it shortly. And then we have a large beaker with tap water and a thermometer that is registering, I'll give you the temperature here, 23.5 degrees Celsius. So if we look at the data table, we're only going to perform one of the trials today, and we'll walk through the calculations, but one trial will suffice for a demonstration. The first row in the data table says mass of magnesium. That's filled in for us, or if it isn't, it's 0.025 grams. So every piece of magnesium that we deal with has that mass. Our water temperature was 23.5 degrees Celsius. And then we'll talk about the barometric pressure when we talk about calculations. let's see if, oh, actually I can find it in a minute here. Now to get the reaction going, I'll remove the thermometer from the beaker. I'm going to set the beaker right about here. And I'm going to put my thumb over the opening of the stopper, the rubber stopper on the eudiometer tube. And I'm going to flip this long skinny tube, and I'm going to put my thumb into the beaker of tap water. And then I'm going to release so that I don't inadvertently release air bubbles into the tube, or hopefully a minimal amount of air bubbles. But what we're looking for is, and this may be hard to see on a video camera, but the acid is starting to make its way down to the bottom of the eudiometer tube. And when it finally comes in contact with the magnesium, the reaction will start. And our evidence of reaction will be the formation of hydrogen bubbles, vigorous formation of hydrogen bubbles. And what we're going to do is gather as much hydrogen gas that we can in the eudiometer tube, and we'll just measure it. Our measurement markings start at the closed end with 1 milliliter, and then it goes down 2, 3, 4, all the way down to 50 milliliters. And I can start to see some bubbles forming. I'm going to move the camera closer so that you can get a better view of this. So now you may be able to see, if you look closely, bubbles forming and moving upwards in the eudiometer tube. And they're going to gather at the top. So they're starting to accumulate here at the top of the tube. And there's lots of little tiny bubbles. Bubbles and bubbles and bubbles and bubbles. Vigorous reaction happening right now. And it's all a matter of the hydrochloric acid coming into contact with the magnesium at the base of the tube where it's anchored. And eventually the magnesium is going to react away. You won't have any magnesium left. It will all have been converted into magnesium chloride and hydrogen gas. The product we can see, of course, is the hydrogen gas, the bubbles. So we're bubbling and bubbling and bubbling. We'll come back in a little bit and give you the final volume. But I did want to give one other piece of information. We have an electronic barometer. So we do need to get a measure of the atmospheric pressure. And because this is a instrument designed to be used in the United States, they give us in inches of mercury for our unit. It's 29.29 inches of mercury. We're going to do some converting when we get to the analysis part of the lab. But for right now, in the data table, you can record in row 3 of the data table, it's going to say barometric pressure. We'll write down 29.29 inches of mercury. So the bubbles are forming. I'll come back in just a minute to give you the final volume reading. But as you can see, the liquid level in the tube is dropping and dropping and dropping as the bubbles displace the liquid. And we'll get our final volume reading at the very end. In fact, I'll just give you that final reading. I'll be looking at the eudiometer tube and seeing what that final reading is. Okay, students, this is the gas stoichiometry lab analysis questions. The amount of hydrogen gas that we collected at the end of the data collection worked out to be as the bubbles were accumulating to be 43.5 milliliters. So then if we take a look at our complete data table, the mass of magnesium was 0.025 grams, the water temp 23.5 degrees Celsius, and the barometric pressure 29.29 inches of mercury, which we'll then have to convert. So let's take a look at the calculations. It said, and there's quite a few steps here. It says first, convert the water temperature from Celsius to Kelvin. In order to do that, we're going to add 273 to our temperature in Celsius. So if in Celsius our temp was 23.5 degrees, we'll add 273, and that works out to be 296.5 degrees Kelvin, which we abbreviate with just a K. Question 2 says, using dimensional analysis, convert the barometric pressure from inches of mercury into atmospheres. And there's 2 conversion factors that they give us in the report. It says 1 inch equals 25.4 millimeters. That's going to be an important conversion. And 1 atmosphere, of course, equals 760 millimeters of mercury. So if we start with what we know from our data table, 29.29 inches of mercury, and we're going to use 2 conversion factors in order to get us to atmospheres. The first conversion factor is that they gave us was 1 inch equivalent to 25.4 millimeters. I'm going to write that so that the inch is in the denominator of the conversion factor, and the 25.4 millimeters is in the numerator. What that'll allow us to do is cross out the unit inches. Next, we know that 760 millimeters of mercury is equivalent to 1 atmosphere. I'm going to write that so that the atmosphere is in the numerator in the conversion factor, and millimeters of mercury is in the denominator. And if you follow what happens to the unit, it's kind of interesting because they're split. The millimeters are here, and the mercury is here. So the only unit not crossed off is atmospheres. So once we've got that worked out in terms of units, now we're going to pull out the old calculator and see what the numerical value is. And I'm getting 0.979 atmospheres. Okay, 0.979 atmospheres for our barometric pressure of 29.29. Question 3, convert the volume of hydrogen gas that was collected into liters. Well, our data table gives us a volume in milliliters. So we'll simply, you can divide by 1,000, or if you prefer, you can show this as a conversion factor, where 1,000 milliliters is equivalent to 1 liter. And if you follow the units here, milliliters crosses out. So it works out to be 0.0435 liters. Effectively, what we did is we moved the decimal 3 places to the left. Question 4. This is an interesting one because it ties into Dalton's law. Whenever a gas is collected over water, as it was in this lab, water vapor is mixed in with the gas you're collecting. So we intended to collect hydrogen gas, but in addition to that, we collected water vapor. In the eudiometer tube, we collected a mixture of hydrogen gas and water vapor. According to Dalton's law, the pressure of this mixture of gases is equal to the hydrogen gas pressure plus the water vapor pressure. So I'm going to write that equation down. The pressure of the mixture is equal to the pressure of the hydrogen, which is what we're interested in isolating, plus the pressure of the water vapor, which we want to subtract out. Your answer to question 2, where you gave the pressure in atmospheres, is the pressure of the mixture. Whether you realize it or not, you collected a mixture of gases. And we're interested in finding the pressure due to just the hydrogen. But if you look at the table in question 4, there's a chart that shows how water vapor varies with temperature. The water vapor pressure is a function of temperature. So our water temperature was 23.5 degrees Celsius. So on this chart, I'm looking here and it's giving us a value for 23 and a value for 24. What I'm going to do is average those two because our temperature is right in the middle. So I'm going to just put an expression here in parentheses where I'm going to state the average of the water vapor pressure at 23 degrees, 0.0294, and the pressure at 24 degrees, 0.0313, and I'll divide by 2 to get the average. All right, so now we'll pull out the calculator. First, I'll average those two numbers. 0.0294 plus 0.0313. Add them together and divide by 2. And I get 0.03035. Then I'm simply going to subtract 0.979 minus that answer. And I get a pressure due to just the hydrogen of 0.94, if I round it, 949 atmospheres. Okay. So we've got the pressure of just the hydrogen. We've got the volume of the hydrogen. We have the temperature of the hydrogen. What do you think is going to come next? The ideal gas law. Exactly. So question 5. For the sample of hydrogen gas that you collected, you now have its temperature from question 1, its volume from question 3, and its pressure as isolated from the water vapor from question 4. Use the ideal gas law to calculate the number of moles of hydrogen gas collected. We'll use our pressure from question 4. 0.949. Our volume from question 2 stated in liters, 0.0435. Number of moles, N, is what we're solving for. The universal gas constant, 0.08206. With its goofy units. And then lastly, our temperature in Kelvin, which was from question 1, 269.5. Now we'll solve for N, the number of moles. And I get a number of moles equal to 0.00187 moles of hydrogen gas collected. Question 6. Here's the beautiful thing. Now we're going to tie it to stoichiometry. For both trials, use stoichiometry and the overall equation for the reaction to determine how many moles of hydrogen will be produced. Magnesium's molar mass is 24 grams per mole. Okay, that's a major hint. And then in question 6, they also give you the balanced equation. Notice that there is a 1-to-1 mole ratio for the magnesium that went into the reaction to the hydrogen that came out of the reaction. So we started this reaction with 0.025 grams of magnesium. And if you follow the balanced equation, for every 1 mole of magnesium that reacts, 1 mole of hydrogen would be expected to be produced. Hold on, before we do that, let's use the molar mass to get from grams to moles. 24 grams of magnesium is equal to 1 mole of magnesium, and we gotta write that so that grams are in the denominator. 24 grams of magnesium for every 1 mole. And then what we were saying before, 1 mole of magnesium is equivalent to 1 mole of hydrogen in the balanced chemical equation. We'd look at the coefficients to find that. And we pull out the old calculator here. And we would expect to produce 0.00104 moles of hydrogen. So our expected production of hydrogen differed from our actual production of hydrogen, not by a lot, but by a little bit. So if we look at question 7, it says, theoretically, your answers to questions 5 and 6 should be the same. Using your answer to question 6 as the accepted value, so our 0.00104 is the accepted, and the 0.00187 as the observed value. Calculate a percent error. Okay, no problem. We put in absolute value brackets. You could go observed minus accepted, or other way around, doesn't really matter. Since it's in absolute value brackets, if it works out to be a negative result, you would just make it positive. And it's all over the accepted. And then to make it a percentage, we multiply by 100. Okay, so now on my calculator, I'm going to take the contents of the absolute value brackets. And we get 0.00083 over 0.00104. And again, multiply by 100 to make it a percentage. And we get 79.8%, right? Which is kind of high. I mean, ideally, students, we would want percent errors kind of in the 20% or lower range, but there are numerous reasons for a source of for results to be what you didn't expect. If you take a look at question 8, it says, give detailed descriptions for one source of error. Explain how this would affect your calculated number of moles of hydrogen, i.e. would the number of moles be artificially high or low? All right, so let's say that we didn't capture, not through any fault of our own, but we weren't able to capture all of the hydrogen. That is, the reaction didn't go to completion. Let's say that was the source of error. And that's something beyond our control. Well, if that were to be the case, then the volume of hydrogen collected, which we measured to be 43.5, would be artificially low. So if we then say, okay, if that number is artificially low, what would happen if we plugged in a slightly higher number? So in question 3, maybe it should be 44 milliliters rather than 43.5. Okay, then our volume of gas collected is 0.044 rather than 0.0435. That would then affect our result in question 5. We would have a slightly higher volume. And if we had a slightly higher volume, you would have a slightly higher number of moles of gas, all other things in the equation being equal. And then if you had a slightly higher number of moles of gas, well, how would that affect your number of moles? It would be higher. And you could do a percent error calculation, but wouldn't necessarily need to. So that would be one example of a source of error and how I would ask you to talk through the calculations to explain why you would have an artificially high or artificially low number of moles of gas. You can come up with your own example, but please give a thoughtful response to question 8. Thank you, students, for your good work.